will deal with the very first unit, that is unit 1, waves. Okay, so in this unit, so as the first slide shows, that we will discuss equation of a simple harmonic wave, particle velocity and acceleration, and wave velocity and particle velocity, and if time permits, we will discuss the differential equation of the wave motion also. I request somebody to mute, and everybody is requested to go to the chat room and write there as present, sir. Okay, so we'll move to the next slide. Now here it is, equation of a simple harmonic motion, and I would like to request you to pay your attention on this figure. Now this figure is representing a wave motion. Actually there are two wave motions. Okay, the wave motion is propagating in the forward direction. Forward direction means in the direction of arrow or in the positive x direction. During its propagation, we find the two waves, one wave that has been started from point O, and the wave whose displacement has been started from point O. Okay, that means it has been started at 0 second. Okay, so it is represented by a thick line curve. So the thick line curve represents a displacement of a particle initiated at time 0 second. Now what about the dotted curve represents the motion of a particle, displacement of a particle which has started after t second. So it has been started at 0 second, and the dotted one represents the displacement that has been started after t seconds. So the displacement of particle O when wave is traveling in the positive x direction, displacement of the particle will be in the y direction. So this is the important thing. So in case of transverse motion, the direction of displacement of the particle is exactly perpendicular to the direction of motion of the wave. So direction of propagation or direction of wave motion is positive x direction, while direction of displacement or displacement of the particle that occurs along y axis. Okay, so this displacement is given by equation of a simple harmonic motion. This is not new to us. We know and we are familiar with this equation. It is simply the equation of a sine wave. So y equal to a sine omega t, where each symbol has its own meaning. Where what is a? A is maximum displacement, or it is also called as amplitude. Okay, if t and what about omega? Omega is called as angular frequency, and small t is time in second. Okay, the time at which we have measured the displacement y, instantaneous time. Okay, if capital T is period of the wave, then okay, let us move first of all for the displacement of the particle which is at point P. Okay, so here now during propagation of the wave is propagating in the forward direction, and during its propagation wave reached to point P. Wave reached to point P, which is at a distance x from point O, from which it is supposed that the wave has been started. So at t equal to 0. So what will be the displacement of the particle at point P? Of course, the particle will lag in phase by certain amount. So there is exactly the phase difference between particle at O and particle at P, because at first the particle at position O has started its motion, and when wave propagates in forward direction and it travels a distance x, at that time, that means after a certain time, the particle at O started the motion, started the displacement, particle at P started its displacement. So particle at P is has started displacement later some after some time, okay, and therefore it lags in phase. And suppose it lags in phase behind the particle at O by some difference of phase, and let it is represented by phi. So if displacement of particle at O along y direction is a sine omega t, then what will be the direction? What will be the displacement of point P? It will be one and same. There will be no change in amplitude, and okay, so there will be change in omega t. What is omega t? It is phase, and that and what the situation tells that P is lagging behind. Lagging behind means the phase will be less. So omega t minus phi. So where phi represent the phase by which particle at P lags behind, okay, the particle at O. So displacement of the particle at point P will be a sine omega t minus phi. Now, uh, we know that the phase difference 2 pi exists for a distance lambda. Where what is lambda? Lambda is wavelength. Lambda is wavelength. We know that, okay, for a wavelength lambda, the phase difference is 2 pi. Now in this case, distance traveled is not lambda but it is x. Distance traveled is x. So what will be the, and the phase difference is phi. So distance traveled is lambda, phase difference is 2 pi, so we have 2 pi by lambda. Phase difference, so phase divided by distance. So in this case, phase is phi, and distance traveled is x. So it is phi by x. 2 pi by lambda, it is equal to phi by x. And from this equation of proportion, we will find the value of phi, and that is equal to what? 2 pi x by lambda. 2 pi x by lambda. Now, what about omega? Omega is the angular frequency. And what is the relation between angular frequency and period capital T of the wave? That is omega equal to 2 pi by T. Omega equal to 2 pi by T. Now, putting equation of phi and equation of omega in previous equation, that is equation 2, we will find that. So, it was what is that equation? Omega t minus pi. So here it is omega 2 pi by capital T into T minus pi 2 pi x by lambda. So 2 pi we can take common. So it is a sine 2 pi in bracket small t by capital T minus x by lambda. Now the relation between velocity v of the wave, frequency n of the wave, frequency in cycles per second or frequency in hertz, where what is omega? Omega is angular frequency, radians per second, and this is what? Frequency in hertz, cycles per second or hertz. Okay, so velocity, if velocity of the wave is v and frequency in cycles per second or hertz is n and wavelength is lambda, then relation between these three quantities is phi equal to n lambda. Phi equal to n lambda. And what is n? N is equal to reciprocal of time period, that means 1 upon t. So if we put here 1 upon t, we find that phi equal to lambda upon t. Phi equal to lambda upon t. So 1 upon t. So what is t then? T equal to lambda upon v. And this value of t we can substitute in equation 3. Okay, so that we will find here. For this, if we put lambda upon v, so v denominator of denominator move to numerator, and here it is vt by lambda. So a sine 2 pi in bracket vt by lambda minus x upon lambda. Now we have a lambda denominator in common, so we take it common, and the equation will be a sine 2 pi by lambda into vt minus x. A sine 2 pi by lambda into v. This is very important equation in the wave motion. This represents displacement of a particle when progressive wave or wave motion travels through the medium. When wave motion travels through the medium, the particles of the medium start their displacement, okay, and the motion of displacement is a simple harmonic motion. So this is expression for the simple harmonic motion, equation of simple harmonic motion, or the displacement of particle of the medium performing SHM when the progressive wave or wave motion is traveling through the medium. So this is called as general equation of This is called a general equation of a progressive wave. And the equation is y equal to a sine 2 pi by lambda into Vt minus x. So general equation of progressive wave. Now here we have considered that the wave is traveling in this direction. That means wave is traveling in the positive x direction. Now if the wave is traveling exactly in the opposite direction, that means in the negative x direction, okay, so from our right hand to left hand in the negative x direction, then simply we have to change the equation, the sign of x, and the equation, general equation of a progressive wave is y equal to a sine 2 pi by lambda into Vt plus x, equation 5. So equation 4, equation 5 are one and same, where equation 4 represents progressive wave, expression, general equation of progressive wave, where the wave is traveling in the positive x direction, while equation 5 represents general equation of a progressive wave when the wave motion or progressive wave is traveling in the negative x direction. So this was about the, what you say, general equation of progressive wave or general equation of SHM. Now the next article which is important, that is wave velocity and particle velocity, and I must tell you here your syllabus starts. Okay, so what I have told you, that was just introduction, and it was it is necessary. The equation y equal to a sine 2 pi by lambda into Vt minus x is very important. And remember, in unit 1 and unit 2 you are writing this equation so many times, and that is the general equation of the progressive wave, where this equation we are using so many times in the next coming this unit as well as unit number 2. Okay, so now look at the figure here, the figure drawn here. Again you will find that there are two wave trains shown by the sine waves, and here the solid line wave train or solid line curve represents displacement of the particle. Okay, particles, they have started their motion at time t1, displacement of the particles at time t1, and the dotted one, which is somewhat later, that is dotted line curve, represents the displacement of the particles at time t2, displacement of the particles at time t2. So the particle who has started its started its motion at time t1 has started from point O. It has started from point O, okay, and it moves a distance OA, and this OA distance is supposed to be x1, and OB distance, and the particle which has started its motion at time t1, represented by dotted curve, okay, has started its motion and reached to point B, and now O distance OB is supposed to be x2. So point A is at distance x1 from O, and point B as is at distance x2 from point O, and both are in the positive x direction. Both are in the positive x direction. So which equation we have to use for progressive wave? That is displacement. For displacement of progressive wave, we have to use equation y equal to a sine 2 pi by lambda into Vt minus x, since waves are traveling in the positive x direction. If though the waves will travel in the negative direction, then we have used the equation y equal to a sine 2 pi by lambda into Vt plus x. Okay, so here, since the waves are traveling in the positive x direction, so we use the equation y equal to a sine 2 pi by lambda Vt minus x for the displacement that has started from O, that is at time t1, we have the distance traveled is x, so displacement at particle at point A, that will be equal to a sine 2 pi by lambda Vt1 minus x1, and for B, it will be a sine 2 pi by lambda Vt2 minus x2. And if both, since both the particles at their mean position, look at here, they are at mean position, that means their motion, their displacement is 0. Their displacement is 0. So this equation equal to 0, this equation equal to 0. So both can be equated. So they are equated. Now after equating, you will find that, so the A, displacement A is the quantity that cancelled out after dividing both sides by A, and both are the sine functions of both sides. If you take sine inverse, you will find that the angles can be equated, and in again angle 2 pi by lambda, 2 pi by lambda cancel, so we have Vt minus 1, Vt1 minus x1 towards left side, and Vt2 minus x2 towards right side. Okay, so if we rearrange this equation, we find x2 minus, so x2 take this side, so x2 minus x1, and here it is vt2, and this will come here with minus vt1. So v takes common, so we will take v common, and it will be v in bracket t2 minus t1. And what is v then? X2 minus x1 upon t2 minus t1. X2 minus x1, this is the short interval of distance traveled between two positions A and B during the progressive motion. And what is T2 minus T1? It is the time required to travel the shortest distance. So short change in distance, short change in time, where dx equal to x2 minus small distance traveled by the wave in the small interval of time t2 minus t1. What is this then? This is the distance traveled, this is the distance traveled, okay, by the wave, and this is the time required for to travel that distance. So rate of change of distance upon, with respect to time, so this represents velocity. So distance traveled by a wave, so therefore this represents wave velocity. Now, what about the particle velocity? As I have told to you, when wave is progresses in the x direction, the particles of the medium start vibrating with SHM along y direction. So displacement of the particle will be along y direction. So similarly, we can write like delta x by delta t as particle velocity equal to delta y by delta t. Remember, here it is y because displacement of the particle is along y axis, where displacement of the wave or distance traveled by the wave is along x axis. Okay, so where delta y is the small distance traveled by the particle in the small interval of time delta t. Now, during interval of time delta t, particle moves from A to B, that means from position A to position B, and at the same time the particle at C will move from C to down to B. See, okay, so I think you are understanding, because particle is traveling in upward, downward, and wave is travel forwarding in this direction. Okay, so when wave is forwarding in this direction and it moves from point A to point B, so particle will start its motion and move in the downward direction at B. From it is from C to B. When wave moves from A to B, particle at C moves from C to B, since displacement of the particle is along y direction. Okay. Now here distance AB, that is the distance along x-axis, that is equal to delta x, and from that equation v equal to delta x by delta t, we have delta x equal to v into delta t. And distance BC is distance along y-axis, and this will be equal to what? Distance along y-axis, this will be equal to what? Delta y equal to u into delta t, because u equal to delta y upon delta t. Okay. Now let us take division of these two. So u into delta t upon v into delta t. So this is simply equal to bc upon ab. Now this bc upon ab, and that is equal to what? Delta y upon delta x. So if you solve this equation, this delta t cancels out. So u by v, this is simply equal to delta y upon delta x. Now what is delta y upon delta x is? See, delta x and delta y, these are very small quantities, infinitesimally small quantities, very small elementary quantities. Small means what? Touching towards 0. So within limit, if delta x tend to 0, delta y by delta x, it is equal to what? What it is known as? This is called as dy by dx. dy by dx. And if you are looking here, it is y intercept, and this is x-intercept of the curve. So this is what slope of the displacement curve we have drawn. Okay, thus u by v equal to dy by dx. So within limit delta x tends to 0, this delta y by delta x changes to dy by dx, and we find that u by v equal to dy by dx besides writing delta y by delta x. Okay, so we take v to this side, you will find the expression for capital U. So u equal to v into dy by dx, where what is u? Velocity of the particle or particle velocity, and what is v? Velocity of the wave or wave velocity, and what is dy by dx? That is slope of the displacement curve. So this is expression for the particle velocity, and it is particle velocity equal to wave velocity into slope of the displacement curve. Okay, so in this way, the relation between, if it is asked to find the relation between particle velocity and wave velocity, you start from the previous slide and reach up to this result and write down this single sentence that particle velocity is equal to wave velocity into slope of the displacement curve. Okay, so here this article ends. Now let us move to the more important equation, that is differential equation of wave motion. See, first of all, we have studied the expression for the, what you say, displacement of the particle performing SHM, okay, and that is to when the wave is propagating through the medium, okay, and then by using that expression we have obtained the particle velocity and wave velocity and a relation between them, and we have observed that particle velocity is equal to wave velocity into uh, the slope of the displacement curve. Okay, now let us find the most again most important equation, that is called as differential equation of wave motion, that describes the motion, that is motion of a progressive wave or wave motion. Okay, again we start from that equation. I have told you that that equation is very important. Again we are starting with this that equation. So what is that equation? Displacement of a particle performing SHM. Okay, and how it is been observed when the wave traveling through the medium, particles of the medium start performing SHM. For example, if wave is traveling through the medium in the positive x direction, then particles of the medium start performing SHM, okay, that is to and fro motion along the y-axis, okay, and displacement at any instant is given by a sine 2 pi by lambda into Vt minus x. Let's call it as equation 1. Okay, now if we differentiate this equation with respect to t, we will find the velocity of the particle. It represents displacement of the particle. Then rate of change of this displacement of the particle will be the particle velocity, that is dy by dt, and this can be simply obtained by differentiating equation 1 with respect to t. Now differentiate. So sine after differentiation becomes cos, and we are differentiating with respect to t, so 2 pi by lambda into Vt, so coefficient of t will be 2 pi lambda, 2 pi v upon lambda, so that coefficient will came in the multiplication, okay, and after that we will find that 2 pi av by lambda into cos uh, 2 pi by lambda into Vt minus x, this will be the expression for velocity of the particle. Now differentiating again equation 1 with respect, differentiating again equation 2 with respect to t, we find rate of change of velocity. And what is rate of change of velocity? That is called as acceleration of the particle. Now let us differentiate this. So after differentiating dy by dt with respect to t, we find d by dt of dy by dt or d2y by dt square, and that is called as acceleration. And since this is a cosine function, the differentiation of cosine will be minus sign. So here it is minus sign. So it is sine. And again, the same coefficient 2 pi av upon lambda will came to multiplication, and it will be, 2 pi v by lambda came into multiplication, this factor, and it will be 4 pi square v square upon lambda square, and this a as it is, and this is the sign. Okay, so this is acceleration of the particle. Let's call it as equation 3. Okay, Now we have two variables here, time and displacement. We have differentiated this equation with respect to t, and now start with the second variable x. So differentiate equation 1, that is equation of y with respect to x, and what we will get, we get dy by dx. And what is dy by dx? We remember, if you remember from the previous article, that is displacement, slope of the displacement curve, or that is also called as compression. And what it will be, it is dy by dx, that is equal to, since we are differentiating with respect to x and x has negative sign, so here it is negative sign, so it will be, and again 2 pi by lambda, x has coefficient 2 pi by lambda, so 2 pi by lambda will came in the multiplication. So in all it will be minus 2 pi a by lambda cos 2 pi by lambda into dt minus x. So this will be dy by dx. Slope of the displacement curve, or it is also called as compression produced in the medium, dy by dx. Now differentiating this again with respect to x, you will find the rate of change of compression when the wave, the medium, when the wave is traveling or propagating through the medium, and that will simply equal to, again, see here cosine function, so differentiation of cosine is minus sign, so one minus negative sign, and again here it is minus x, so another negative sign. Okay, two negative signs, and here it is one third one, so three negative signs, we will have negative sign here. Okay, and the common factor is 2 pi by lambda. Okay, 2 pi by lambda, so here it is 2 pi a by lambda into 2 pi by lambda, so minus 4 pi square a by lambda square, and here cos differentiated to sine, so this will be the equation for rate of change of compression. Now the part is over, you have to simply equate first differentiation and equate second differentiation. You will find the two important equations. So equating first differentiation, that is equating equation 2 and equation 4, you will find that dy by dt is one and same by dy by dx, only the factor is minus v, that we have to take common, and we will find here dy by dx. So dy by dt equal to minus v into dy by dx. This is one equation. And another very important equation that has been obtained by comparing equation 3 and equation 5. Equation 3 is for d2y by dt square, and 5 is for d2y by dx square. You will find that the only the difference is v square. So there is also negative sign in equation 3. So no matter of the negative sign, so we will find the equation as d2y by dt square equal to v square into d2y by dx square. And this is the very important equation, and this is called as differential equation of the wave motion. This equation can be used to explain the, what you say, uh, wave motion or progressive motion. Okay, so here we end